have to have placeholders, no matter what. Okay? So you're trying to divide a third-degree polynomial by a second-degree polynomial. The third-degree polynomial should have how many terms in it as after you write it out? It should have 4. It's always n plus 1. The second-degree polynomial should then also have n plus 1 terms as well, so it should have 3 of them. Okay? So I don't need a placeholder for the x cubed and stuff. But I need a placeholder for the x squared. Okay? I need to put a placeholder there. And then you just go through the question. What do you multiply x squared by to turn it into x cubed? X. So since I only have to multiply by a single x, not an x squared or anything, I just place it above the x. Because now, did you not put a placeholder? Yeah, that's why. So see how by putting a placeholder there, when you multiply 3 things out, look what happens underneath here. You get 3 things here. Yeah. That's how you're able to make this stuff completely go. That's the importance of having to have a placeholder no matter what, whether it's in between x squared and a constant or it's the constant itself. You still gotta have a placeholder to make it work. That's like the only real rule of this. Then as you go through it, it's not terrible. You got x cubed, 0x squared, and a 5x. 3 subtraction problems. The x cubed goes away. 8x squared minus 0x squared is just 8x squared. Negative 3 minus 5 is a negative 8. Excuse me. X, and then bring down the 16. And then what do you multiply x squared by to turn it into 8x squared? 8. Very good. So you multiply it, is it positive or negative? Positive, good. Keep signs that way, because when you want to multiply it out to become the exact value, so that way when you subtract, it goes away. Okay? Whether it's positive or negative. So we're going to get 8x squared, a 0x, and a 40. Back all of that out, and you get negative 8x minus 24, I believe. That's now the remainder. Okay? That's now the remainder. So I put that, what was the sign of that? Negative. So I bring that up, I go minus, this goes in the numerator, 8x minus 24, all over x squared plus 5. When I do my remainder, I don't have to put that placeholder there. It's okay. If you put it in there, that's fine. It's not a big deal. Sometimes, depending upon what answer values you check, they might distribute some of the negatives back and forth. So if your signs were a little bit weird in the numerators, that's usually the reason. I think a lot of times the textbook will do a plus remainder, and then they just leave like the negative 8x minus 24, or they might take out the whole negative and write it in parentheses at 8x plus 24. It just depends on what they're doing. Okay. For us, what I've been showing you guys, just to write it down with whatever the sign was up in front and then making the fraction, perfectly fine, and that's going to work for us. Okay, it's going to work out just fine. All right. Do you want to do another one, just because I know we flew through that in like about 7 minutes? What do you got? Sure. I'll get you next one. All right, 4th degree polynomial divided by a 3rd degree polynomial. So the 4th degree polynomial has to have how many terms? 5. The 3rd degree polynomial has to have how many terms? 4. Okay. So it works out, this is just giving me a little messy looking. So I know on the outside it'll be x cubed, x squared, a 0x minus 5. Then we have a 2x to the 4th, 2x to the 3rd, a 0x squared minus a 10x and minus a 9. And now, what do you multiply x cubed by to turn it into 2x to the 4th? 2x, good. And again, notice I'm going to put it above the x value. So if I put a 2x here, when I distribute out to those 4 parts, these 4 pieces will go away. What's wrong? Maybe something did. Oh, yeah, that's 3. I know. It's really easy numbers that you write backwards. They work well. Right? It's what? Is it? Yes, it's 3. And weren't you yelling at someone for that exact problem? Anyway, so now distribute through that 2x. We're going to get 2x to the 4th. 2x cubed. 0x squared minus a 10x. And then when you back all of it out, I can see why you're kind of like, what do you do now? Bring that down. That's just your remainder. That's just your remainder then. Oh, you want to? No. Oh, which one? This one? Okay. Remember, what do you have to multiply x cubed by to turn it into 2x to the 4th? That's what you're asking yourself every time. Every time as you do long division, you're always trying to eliminate that or that very first term of wherever you're at. Whether it's the first one to go in, or as we were doing last week, each time through we were eliminating that first term. So every time you're trying to eliminate that first term by figuring out what you're multiplying at the top here, that's what your goal is. It's a little bit different than when you're doing just regular division, like how many times does 7 go into 12? This is, I want to eliminate that value by using exponent rules of multiplication and subtraction. Okay, that's what that's different. You had another question though, what was it? Oh, okay. Did that help for 26 then? Excuse me. All right. Any others? Or did you have a chance? Yes, sir. I have a squared term, which means how many as of right now, when I was piecing this one together, I was anticipating that we would have gotten just a smidge further. You can't do this one. Okay? Did you try to group it with threes and threes? You could kind of get through it if you group them as two trinomials. But because there's a different way to do that one. For us right now, for us to be able to factor and do things, we have to be able to do stuff that looks like number 20, number 19, 21 is okay. 20, oh, these are that's just tail dancing stuff. 26. Factoring these guys, 4 terms, 3 terms. Yes, these guys are okay. These guys are all okay. But unfortunately, as of right now, you haven't learned how to do that completely. Because there's a really nice shortcut that we'll start talking about. We'll briefly look into it Wednesday about how you align yourselves with possible zeros. Actually, no, we won't get to that on Wednesday. I'm sorry. We'll be giving values. It'll be next Monday when we start talking about possible zeros. This one just accidentally got thrown in there. Plus you. Yeah. Because this one here, you don't have to write this down. What you wind up having to do is, what are your factors of 4? What are all the factors of 4? 1, 2, and 4 pluses and minuses. So like negative 1, negative 4, positive 1, positive, things like that. What are all the factors of the leading term coefficient? 1. So the possible zeros that you could have that would make this work would have been plus or minus 1, 2, and 4. So what happens is we're going to use synthetic division to factor by breaking down a larger polynomial into smaller chunks. We're not quite there yet. I wasn't sure how far we get when I just hit the button of finding zeros. It's not a big deal. Yes, sir. Yeah, what do you got? Yep. As long as it's polynomial, it works. It's an awesome tool to use for factoring. It really is. Okay. Okay. Don't worry about 22, guys. I have nothing like that on there. I've got 4-term stuff, 3-term stuff, GCFs, things like that we've been working through. This one you had to know a little more information. We just hadn't gotten that far yet. We're a little bit behind where I thought we would be as of going into this year right now. So it's not a big deal. I wouldn't worry about that. Excuse me. What else did you have going on in here that you wanted to? Yes, sir. Oops, slide this up here. The multiplicity. Okay. The reason they have multiplicity here is, well, what's your first rule of factoring? GCF. When you take the GCF out, you've got an x squared. Then you've got x to the third, 5x squared, 3x, and a 15. Now it's forcing you to group. Okay. All the while, this x squared stays outside. So this x squared is still out here. I'm going to group these guys and get GCFs again. In doing so, I get an x squared, and I have an x plus 5, a positive 3, and an x plus 5. So far, so good? Are the two things in parentheses the same thing? That's a very good sign, so you rewrite that down. Excuse me. Right now I have an x squared, I have an x plus 5, and then what's left? X squared plus 3. Now, if I'm going to find all of my zeros in this one, well, I have 3 zeros that are real and 2 zeros that are imaginary. It's a 5th degree polynomial, so I should have 5 zeros. My imaginary ones come in here at the x squared plus 3. So those will be at plus or minus I root 3. Are we okay with that? The next one is at negative 5. And here is x squared. X squared is represented by what times what? X times x. Okay. So that's the idea of this is a 0, but it's twice. So that's why it's got multiplicity. So your zeros are 0 with multiplicity multiplicity of 2, and then -5 plus or minus I root 3. That's where it comes in the idea of why they write it as multiplicity. Okay. And usually that's the style you'll see when you take an x squared out right away. That's where you're going to get multiplicity. Okay. Yep, and that's one of the zeros. I believe the way I wrote it on it for tomorrow, I said state any multiplicities if needed, and that would be how you would write that. Okay, does that make sense? We were doing that in class the other day. We would say 0 multiplicity of 2. I mean, if you want to write multiple 2, I'm okay with that. Save me a little handwriting. Tails, that's all I want. Because I'm not going to let you use the graphing calculator tomorrow. I'll give you a regular one, but I'm not going to give you a graphing calculator. That's too much. Yes, sir. Yeah. Sure. Absolutely. Which one do you want to see? Either one? Doesn't matter? Okay, they're both kind of the same, so let's do 17. So this is number 17 on here. Find a factor. Okay, but it says equals 0, so we gotta get our zeros. So in this case here, it's an 8-degree polynomial, which means how many zeros should it have? 8. It's always nth degree polynomial, n zeros. Excuse me. See how it's written as a trinomial? It goes 8, 4, exponent of 1. Every time the exponents get cut in half as they're going down, or divided by cut down in half like that, it goes 8, 4, then nothing. That just means that you can factor it like you would a quadratic. And think of it as what times what 16 you add together to get -17. -16, -1. Very good. But then you would write it as x to the 4th minus 1, x to the 4th minus 16. See where I'm going with that? Does that make sense now? Yes, sir. Exactly. So I branch out a little bit further because is x to the 4th a perfect square? Is 1 a perfect square? Is that a subtraction symbol? Yep. So I've answered yes to all those questions, which means I can rewrite it as x squared minus 1, x squared plus 1, and I can do the exact same thing with the x squared minus 14, and I'll get 60, sorry, x squared minus 4, x squared plus 4. At this rate, or excuse me, at this point, you can kind of, if it is, since this says just equals 0, which means find zeros. Whenever you see an equals 0 part, means you need to list out your zeros. So here, can't I just start writing all my plus minuses? Because what are my zeros in x squared for x squared minus 1? Isn't that just plus minus 1? Isn't this plus minus I? Remember, you're setting each one of them equal to 0. Okay? When you get down to a squared term like that, you can do that. If it says just factor, then you'd have to write out x plus 1, x minus 1, leave it as x squared plus 1, x plus 2, x minus 2, and leave it as x squared plus 4, because you can't factor that any further. But since it has an equals 0 part, that's why we take it that step further and list them all out. So then we have plus or minus 2 and plus or minus 2. And that's a good sign because we have 8 zeros because we have an 8th degree polynomial. And 18 is basically the exact same thing, but it's 25 and -1. Okay. I'm sorry, negative 25 and -1 for 7. Does that help on that? Yeah. Perfect. Spell. Which one are you looking at? Oh, 17? Yeah, this one I would have, it was when I printed this from the CUDA stuff, it just said factor and it equals 0, so that just means get a 0. On anything that I give you as far as assessment-wise, I will say find all zeros, list multiplicities. So as soon as you see equals 0, you just get to getting me all of my zeros. If you get to the point here where you don't need to write it as x plus 1, x minus 1, if this was just that and it said factor, then you'd have to write x plus 1, x minus 1. You can't do anything. X plus 2, x minus 2. You can't do it. To be honest with you, more often than not, I will probably have you finding zeros because in the grand scheme of things, that's where we're heading. To be able to plot zeros and do dance moves and know where change directions are occurring and be able to go that route. Factoring is great, it's fine and dandy, but we want to make sure we know where we're heading towards. Does that make sense? If you're looking at like, if you look up to like number 12, that's a factor problem. There's no equal to 0 there. That one, you'd have to go through the process of doing your difference, sums or differences of cubes. Correct. Yep. If there's an equal 0, then you give me zeros. So if we look at number 12 says 250, excuse me, x cubed plus 2. So that means that this one is going to be your sum of cubes. But remember, what's always your first rule of factoring? GCF. What do these two numbers have in common? 2. So I bring out a 2, and I have 125 x cubed plus 1. Now, this means, well, actually, let me ask this. What's the cube root of 125? 5. That one's pretty odd. I'm hoping you guys realize that the cube roots that they're asking you to do are pretty straightforward. 27, 125, things like that. So that means that this is the pattern, 5x quantity cubed plus 1. That's that's the value of a and b. So your pattern for this, remember, is a plus b, a squared minus ab plus b squared. So I have to basically break that into those two parts. All right. When I do that, I still have my 2 out front. I get 5x plus 1. And then what's the quantity 5x squared? 25x squared. Remember, when it's jump squared, it means jump times jump. So we just write it as 25x squared. And then it's minus 5x, to multiply the 2 together. And the last one is just plus 1 because it's 1 squared. That would be fully factored form. You're done. Okay, you're done. What changes if it says that? Then you got to find your zeros. Okay. Does that scalar of 2 have any bearing on the problem anymore? Nope, not at all. So then I have to take my terms, the 5x plus 1, set it equal to 0. 25x squared minus 5x plus 1, set that equal to 0. Well, one of those is pretty easy to do. Woohoo! Negative 1/5. Subtract and divide. The other one, what did I tell you guys you have to do when you have to factor that one? Quadratic formula. Okay. If you have to find zeros after doing a sum or a difference of cubes, you always have to use quadratic formula for that trinomial, because that trinomial will not be factorable. Okay? So use quadratic formula real quick. Opposite of b plus or minus square root b squared minus 4ac 2a. So let's see here. We get 5 plus or minus the square root of 25 minus 4 times 25 times 1 all over 50. What's 4 times 25? It's 100. What's 25 minus 100? Negative 75. So you start to see this, as awful as it started, it's not that bad. Because what's the perfect square that's hiding in 75? 5. Right? So isn't 75 5 root 3? But since it was negative, what do I have to bring out? An I. Yep. So I wind up getting 5 plus or minus 5i root 3 all over 50. And you can take out a GCF. At this point, more often than not, with those trinomials like that, there's going to be a GCF. And here's the thing. You can't just take the 5 over the 50 and write it as 10. You have to take 5 out of everything. Okay? You have to take 5 out of everything. What are we going to ask? Yep. Because if you think about this, isn't this the same as saying 5 times the quantity 1 plus or minus I root 3 over 50? That's where that comes from. Because within the numerator, you can factor out the GCF of 5. Okay? Because now what's 5 over 50? 1 over 10. So this would simplify out to being 1 plus or minus I root 3 over 10. There's 2 zeros. There's another one. It was a third degree polynomial. So it should have 3 zeros. Just so happened one was real, the other 2 were imaginary. Okay? That's where that comes into play. That also means that the graph of this probably doing that. Or it just went through the axis once. Yes, sir. Sure. Number 10. Is that, Bell, I know that was a little bit more from the 0 stuff when we were talking earlier, but that's completely possible for me to ask. Don't forget quadratic form, it's kind of an important thing. 10 you were saying, Tom? All right. 7x cubed 42x squared plus x plus 6. This is a straight factor problem. I changed the b's to x's because x marks the spot. Not really, but sometimes, you know. 4 terms. Whenever you have a 4-term polynomial, you always want to try and see if you can factor it via grouping to start with. So you group the first 2. What do those guys have in common? 7x squared. Good. So I factor out of 7x squared. I'm left with x plus 6. What do those guys have in common? 1. Good. Factor out of 1. And I'm left with x plus 6. Are those 2 things in parentheses the same thing? Yes. Good sign. Write it down. What are you left with then? 7x and a 1. 7x squared. Excuse me. That is, this is number 10? Yeah. So this is a straight factor problem. What would change if I said equal 0? We just find the zeros, okay? So the only thing that winds up being weird here, well, this one's easy, is when you have to get the 0 for the 7x squared plus 1. Which means you have to rationalize your denominator because it's the square root. Okay? So just for a reminder, 7x squared equals negative 1 divided by 7. I get x squared equals negative 1/7. You okay with that? Subtract and divide. Take the square root over an equal sign. It's going to be a plus minus. And I'm going to write it out as 2 separate square roots real quick. What's the square root of negative 1? I. Good. All right, so my numerator becomes I over root 7. It's not too bad at this point, because what do you have to multiply top and bottom by to get rid of the root? Root 7. Okay? So if you multiply the top and bottom by the root 7, we're going to wind up with x equaling plus or minus I root 7 over 7. Remember, that's how we rationalize out to get rid of the radicals within the denominator, just by multiplying top and bottom by whatever the root was. Okay. Yes, ma'am. It's just tails. Tails. We haven't, I've alluded to enough of how changes the direction and all that kind of get into it. We haven't studied it enough to know why. And I'm just preemptively getting you towards the idea of what things are going through. So if you can do tails, just go. Yeah. Just tails. I'm just gonna ask you for sketching tails. Again, it kind of goes along with what you were just asking, is we haven't had enough time yet to be able to do general shapes. We're getting there. We're a little bit behind where, when I made this sheet before, where we were before. So it's just the idea of, if you know what your tail dances are doing, you're gonna be fine. Because as we continue building out for the second half of this unit of polynomials, that's when everything starts going. In years past, when we've gotten to this part, we've done a little bit of that already, but we're just a couple of days behind where we were at before. So it's no big deal. We're just problems that we're just adapting to what we can do. Yes, ma'am. Yeah, we'll do it tomorrow. We can do it tomorrow, and then on Wednesday we'll start doing some more of the synthetic stuff, and then on Thursday on the half day we'll be able to. We'll probably be able to start talking about. Remember that the question what was on here? 22, I think you guys first had. Remember how I started to show you why your possible zeros were 1, 2, and 4. On Thursday we will talk about how we set those things up and how we can list our possible zeros. I don't think we'll do anything because it's short and then it goes into a longer weekend. I think what we'll wind up doing is just talk about possible zeros, and then we'll start building next Monday into finding the zeros from the possible lists. It's a pretty easy process, to be honest with you. It's a good thing for a half day. What else you got on here? Anything? Exponent rules. The only other thing that was that first section we did about the exponent rules, power to power, things like that, simplifying monomials and stuff. That was what, 6.1, I think. Does that sound about right? So anytime, trying to think. Excuse me. Oh my nose. Yeah, it's ones like these. Remember just using your exponent rules. They weren't very difficult.